So, hello students, welcome to Samodpuri Pathshala. Now we will discuss about algebra of linear transformation, IN Hostin book theorem. So, first, homomorphism of V, V is an associative ring with unit element under operation addition U T1, T2 equals to UT1 plus UT2, and in multiplication V T1 T2 equals to V T1 bracket होल इंटू T2। सो अगर इसका प्रूफ हम देखेंगे, हालांकि इसका प्रूफ नहीं पड़ता है, तो फिर आप अपना कॉन्सेप्ट क्लियर के लिए देख लो। सो सिंस T1 बिलोंग्स टू होमोमॉर्फिज्म ऑफ V, T1 is mapping from V to V, which implies U plus VT1 equals to UT1 plus VT1. Similarly, alpha UT1 equals to alpha UT1. And if T2 belongs to homomorphism of V, or T2 is mapping from V to V, U plus V T2 equals to UT2 plus VT2, and alpha U T2 equals to alpha whole bracket UT2. Then T1 plus T2 belongs to homomorphism of V, and we have already proved that homomorphism of V is an abelian group under operation. So now let us discuss what is algebra. An associative ring A is called an algebra over F if A is a vector space over F such that for all A, B belongs to A and alpha belongs to F, alpha AB equals to alpha whole bracket B is equals to A alpha B whole bracket. Proof: we have already proved homomorphism of V is associative ring and homomorphism of V is a vector space over F. To prove alpha T1 T2 equals to alpha T1 T2 equals to T1 alpha T2. So let V belongs to V, small v belongs to V. This is a small v alpha T1 T2 equals to alpha V T1 T2, which imply alpha VT1 T2 is which equals to V alpha T1 T2 V alpha T1 T2। इसके ब्रैकेट में आप अदला बदली कर सकते हो, and this is same also as it is. So homomorphism of V is an algebra over F. Okay, this is also not important question, ये आप एग्जाम में नहीं पड़ेगा आपका ये। ओके, अब हम स्टार्ट करेंगे अपना इम्पोर्टेंट क्वेश्चन। सब ये है इम्पोर्टेंट थ्योरम, डायरेक्ट पड़ेगा क्वेश्चन में। ओके, सो थ्योरम में गिवन है इफ ए इज एन algebra with unit element over F, then A is isomorphic to subalgebra of A of V for some vector space V over F. Let us take V equals to A. For each A belongs to A, define TA is mapping from V to V by VTA equals to VA. Let UV belongs to A and alpha, beta belongs to F. So U plus VTA equals to U plus VA, which equals to UA plus VA, which equals to UTA plus VTA. Then for this alpha UTA equals to alpha UA, then alpha UA ब्रैकेट में अदला बदली करके ये आ जाएगा। So therefore TA is linear transformation of V to V. Therefore TA belongs to A of V. Then now define psi is mapping from A to A of V by A psi equals to TA. Claim psi is a vector space homomorphism. So alpha A plus beta B whole psi equals to alpha A psi plus beta B psi, and alpha A plus beta B psi equals to alpha A psi means TA and beta B psi means TB. So A alpha TA plus beta TB. Then next, our next claim is psi is ring homomorphism. Then we can prove by this AB का whole psi equals to A psi B psi. A psi B psi means TA TB. Okay, Then our next claim is psi 1 to 1. So to prove kernel of phi equals to 0, suppose A belongs to kernel of phi. So A psi equals to 0, TA equals to 0, then VTA equals to 0, ETA equals to 0, and EA equals to 0. So kernel of psi equals to 0, then psi 1 to 1, and psi of A to A of V is an isomorphism, which completes our proof. So let A is an algebra with unit element E over F, and let Px equals to alpha 0 plus alpha 1 x1 plus alpha 2 x2 plus dot dot alpha n xn be a polynomial in Fx. If A belongs to A, then Pa equals to alpha 0 plus alpha 1 a1 plus alpha 2 a2 plus alpha n an. If Pa equals to 0, we say that it satisfies P of x, or we can say that P of A is a minimal, we can say P of x is a minimal polynomial of P of A. So our next lemma is let A is an algebra with unit element over F, and suppose that A is of dimension m over F, then every element in A satisfies some non-trivial polynomial in f of x of degree at most m. So let E be the unit element of A. Let A belongs to A where A not equals to E. So consider the set M E a square up to A to the power m. Since M contains m plus 1 element, so dimension of A equals to m, small m, and m is linearly dependent. Therefore, there exist scalars alpha 0, alpha 1, alpha n, not all 0, so that alpha 0 E plus alpha 1 a1 plus alpha 2 a2 plus alpha m am equals to 0. This is P implies A satisfies a non-trivial polynomial. So P of x equals to alpha 0, alpha 1 x1 up to alpha m xm of degree at most m. So now next theorem is if V is n-dimensional vector space over F, then given any element T in AV, there exists a non-trivial polynomial Qx belongs to Fx of degree at most n square. This also easy. So given V is a finite dimensional vector space over F of dimension n, then A of V equals to homomorphism of V comma V is of dimension n star n equals to n square. Also A of V is an algebra with unit element. So by above lemma, for each T belongs to AV, there exists a non-trivial polynomial Qx belongs to Fx of degree at most n square, so that U of T equals to 0. So definition of minimal polynomial, now let us see. Let V be the finite dimensional vector space over F, and let T belongs to AV. A polynomial Px belongs to Fx is said to be minimal polynomial for T if it is a non-trivial polynomial of lowest degree such that P of T equals to 0. If T satisfies the polynomial h of x, and if Px be the minimal polynomial of T, then P of x divides h of x. So right invertible means an element T belongs to AV is called right invertible if there exists U belongs to A of V, so that TU equals to 1. अगर TU equals to 1, so right invertible, and UT equals to 1, so left invertible. And invertible means TU equals to UT equals to 1 when that is your both invertible and both left invertible and right invertible. What that is T. And singular, an element in A of V which is not regular, it is called singular. If V is finite dimensional vector space over F, then T belongs to AV invertible if the constant term of the minimal polynomial is, when the polynomial for T is not 0. So prove let T belongs to AV and P of x equals to alpha 0 plus alpha 1 x1 plus alpha 2 x2 plus dot dot alpha k xk be the minimal polynomial for T over F. To prove alpha 0 not equals to 0 if and only if T is invertible. Let us first suppose that alpha 0 not equals to 0. Since Px be the minimal polynomial for t, which implies P of t equals to 0, that is alpha 0 plus alpha 1 t plus alpha 2 t square plus dot alpha k tk equals to 0. These imply alpha 1 t1 alpha 2 t2 plus dot alpha k tk equals to minus alpha नॉट. अगर ये माइनस अल्फा नॉट बोथ साइड डिवाइड कर देंगे तो ये आ जाएगा देन टेकिंग टी ऑन आउटसाइड तो टी एस इक्वल्स टू एच टी इक्वल्स टू 1. Hence t is invertible. Now t invertible we have to prove that alpha naught not equals to 0. Then we prove this by contradiction. Suppose alpha 0 equals to 0, then p of x equals to this and p of t equals to 0. So p of t equals to alpha 0 यहाँ पर नहीं रहेगा. So 0 equals to alpha 1 plus alpha 2 t1 plus alpha k tk minus 1 t. Then t inverse exists. Then t inverse exists. So post multiplying both side by t inverse. Post multiplying both side by t inverse, we get alpha 1 alpha 2 t1 plus dot alpha k tk minus 1. So let qx equals to this. Then t satisfies qx of qx whose degree is less than that degree of px, which is a contradiction. So px is a minimal polynomial for t, which imply alpha not equals to 0. Then our next corollary given that if V is finite dimensional over F and if T belongs to AB is singular, then there exists an S not equals to 0 in A of V such that St equals to Ts equals to 0. So prove let T belongs to AB is singular, which implies T is not regular. By previous theorem, if T is not invertible, then the constant term of the minimal polynomial is 0. So P of t is alpha 1 t1 up to alpha k tk equals to 0. Then alpha 1 plus alpha 2 t1 plus dot alpha 2 tk minus 1 equals to 0. So let s, this part is s and s not equals to 0. If s equals to 0, then it will become minimal polynomial for t, which is a contradiction to the definition that t is a minimal polynomial. Now st equals to 0. So st equals to ts equals to 0, which completes our proof. So next proof is if V is finite dimensional over F and if T belongs to AV is right invertible, then it is invertible. Let T belongs to AV is right invertible, then there exists U belongs to AV such that TU equals to 1. This is for right invertible. To prove T is invertible, suppose not that is T is not invertible, then T is singular. Then there exists S not equals to 0 in AV such that TS equals to ST equals to 0. So St of V equals to 0, that is St of V means this is your St, that is your T of V means left invertible. Okay, that is your St of V is right invertible. TV means क्या left में T है तो it is right invertible. So S dot 1 equals to 0, which implies S equals to 0, which is a contradiction to the fact that at not S not equals to 0. So therefore T is invertible. Then now comes to next corollary. If V is finite dimensional over F and if T belongs to a V is invertible, then T inverse is a polynomial expression in T over F. So proof may let T belongs to a V is invertible, then if Px is this, then minimal polynomial for T, then P of T equals to 0. Then अगर हम T को कॉमन लेंगे अल्फा 0 बाई टी अल्फा 1 t1 अल्फा 2 टी स्क्वायर ये हो जाएगा. देन अल्फा 0 टी इनवर्स इक्वल्स टू 0. देन टी इनवर्स इक्वल्स टू माइनस 1 बाई अल्फा नॉट. बस टी इनवर्स एक्सप्रेशन हो गया ये. देन कम्स टू नेक्स्ट. if V is a finite dimensional over F, then T belongs to AB is singular if and only if there exists V not equals to 0 in V such that Vt equals to 0. सो ये एक फिर नया केस है if V is finite dimensional over F, then T belongs to AB is singular. सिंगुलर वहाँ पर क्या होता था, एस टी इक्वल्स टू टी एस इक्वल्स टू जीरो, और यहाँ पर क्या है, वी टी इक्वल्स टू जीरो. सपोज दैट टी बिलोंग्स टू ए बी सिंगुलर बाय थ्योरम, मैंने जो कहा अब एस टी इक्वल्स टू टी एस इक्वल्स टू जीरो. Since S not equals to 0, then there is an element W belongs to V such that WS not equals to 0, then V equals to WS, then Vt equals to WST, and W of ST W dot 0 equals to 0. Then there exists a non-zero vector V belongs to V such that it is annihilated by T. Okay. Similarly, conversely, if Vt equals to 0, we have to prove that T of AB is singular. Okay, so Tv equals to 0 or Vt equals to 0, no problem. So to prove T is not invertible, that is T is singular. Suppose T is invertible, then the constant term of the minimal polynomial is not 0, then Pt is this much. In particular, alpha 0 plus alpha 1 T1, this is your Tv equals to 0. Okay, from this Tv equals to 0, then alpha 0 V equals to 0, and this the all term Tv is 0, then alpha 0 equals to 0 and V not equals to 0, which is a contradiction. Thus T is not invertible, that is T is singular. So what is the range of T? Now the definition comes. So if T belongs to AB, then the range of T is defined by Vt equals to small vt such that V belongs to V. If V is finite dimensional over F, then T belongs to AB is regular if T maps V onto V. So प्रूफ में हुआ if T belongs to AB is regular. पहला केस में क्या था, that is your constant term of the minimal polynomial are not 0, and यहाँ पर है if and only if T maps V onto V. Let T belongs to AB is regular, then T inverse exists. Let V belongs to V, then T inverse V belongs to also V, then T inverse V equals to V, which implies TV equals to V, which implies T is onto. Then conversely, suppose T is not regular, that is T is singular. If V is a finite dimensional over F, then there exists V belongs to V such that TV equals to 0. Therefore, there exists a V1 belong to V such that TV equals to 0. This V1 can be extended to the basis, say V1, V2 up to Vn, and every element of Vt is a linear combination of V1t equals to W1, V1t equals to W2, that is your V2t equals to W2, dot Vnt equals to Wn, as W1 equals to 0, so V1t equals to also 0, which implies Vt is spanned by n minus 1 element. अगर V1t not equals to 0, so Vt is spanned by n elements. If V1t equals to 0, then Vt is spanned by n minus 1 element. Therefore, dimension of Vt less than equals to n minus 1 less than equals to n, which equals to dimension of V, which implies Vt not equals to V, which implies T is on 2. Okay. So मिलते हैं अगले वीडियो में. नेक्स्ट आवर पार्ट इज कैरेक्टरिस्टिक रूट्स का थ्योरम. अब हमने कवर किया एल्जेब्रा ऑफ linear transformation theorem. So thank you for watching this.